Continuing with the section 3.5 notes, we now conclude with example 4, solving a fifth degree polynomial equation. The graph of the polynomial is shown in the notes, and from the graph it would appear that -1 is definitely a solution. It is an x-intercept, so -1 would appear to be a 0, therefore a solution of the equation. The question is, can we find any others? What I'm going to do first, to just kind of get a starting point for solving the equation, is to list the possible rational zeros of this fifth degree polynomial using the rational zeros theorem. So for that purpose, we need to identify the constant term, which is 2, the leading coefficient, which is 1. We need to list the p's and the q's. The p's are the divisors of the constant term 2, plus or minus 1, and plus or minus 2. The q's are the divisors of the leading coefficient of 1, plus or minus 1. The possible rational zeros of this polynomial then would be all possible p over q's. That would be plus or minus 1 or plus or minus 2. Only 4 possible rational zeros. As you can see, -1 is one of those possibilities. The other 3, positive 1, positive 2, and -2, based on what we can see in the graph, do not appear to be rational zeros themselves. Let's test that -1 actually is a rational zero by dividing its factor x plus 1 into the polynomial using synthetic division. And so for that we would use -1, and then the coefficients. Notice there are no missing powers of x, so no need for any zeros. So the leading coefficient is 1, the coefficient of x to the fourth is 1, coefficient of x to the third is -1, coefficient of x squared is 1, coefficient of x is 4, the constant term is 2, and we can begin our synthetic division. Bring down the 1, multiply, add, multiply, add, multiply, add, multiply, add, multiply. And indeed we see that -1 is a 0, x plus 1 is a factor. Okay, now the problem is that at this point the quotient we obtained in the bottom row is a fourth degree polynomial. It's x to the fourth minus 1x squared plus 2x plus 2. And actually, I'm not sure, it might be possible to do something with that just using ordinary factoring, but generally speaking, we're going to have some problems dealing with a fourth degree equation. What we can do here, however, is notice something about the graph around -1. You see how flat the graph gets there? The fact that the graph is flattening there suggests that -1 has a multiplicity greater than 1. The greater the multiplicity of a zero, of a real zero, the flatter the graph gets as the graph goes through the x-axis. So this suggests that perhaps we can use -1 a second time, dividing it into the previous quotient. So let's bring down 1, multiply, add, multiply, add, multiply, add, multiply, add, and indeed, -1 worked a second time. Well, guess what? It will even work a third time. And the reason I know that is that the graph flattens as it goes through, but it doesn't just touch at -1, it actually crosses through the x-axis. And that only happens when the multiplicity of the 0 is odd. So this could not be an even multiplicity 0. It has to be an odd multiplicity 0. It probably is multiplicity 3. So if it's multiplicity 3, we should be able to do one more synthetic division using -1. Let's see if it works. Bring down 1, multiply, add, multiply, add. Yes, it does. Okay, so what we've done is, from a 5th degree polynomial, completed 3 synthetic divisions. The first quotient we obtained would be, that's this one right here, would be have degree 1 less than the original polynomial, so that would be 4th degree. The next quotient should have a degree 1 less than the previous quotient, so that should be 3rd degree. And the next quotient should have degree 1 less than the previous one. That would be 2nd degree. In other words, what we have at this point is a quadratic factor, a 2nd degree factor at the bottom. So what we've done is taken this equation and essentially found that x plus 1 occurs as a factor 3 times with a remaining factor of x squared minus 2x plus 2. In other words, x plus 1 cubed times x squared minus 2x plus 2. So any remaining zeros, any remaining solutions should come out of that remaining quadratic factor. So let's see if we can find any remaining solutions. Well, it's a quadratic equation, so let's try, excuse me just a moment. Let's try the quadratic formula. I can tell you that x squared minus 2x plus 2 does not factor. You can check that for yourself using basic methods, that is. So the quadratic formula, again, I'll write it down. It's minus b plus or minus square root b squared minus 4ac over 2a. Here we have a equal to 1, b equal to -2, c equal to 2. Let's plug those values in. Excuse me, just a second. All right, so x would be minus b is 2 plus or minus square root of b squared, -2 squared is 4, minus 4, a times c is 2. I thought I had paused it. I didn't. Glad I didn't say anything. A times c is, I'm having a little trouble with my computer, which I always seem to have at the end of the notes that I'm doing. All right. Divided by 2 times a, which is 2 times 1, which is 2. And then I want to simplify this. So that's 2 plus or minus the square root of 4 minus 8. over 2, or 2 plus or minus the square root of negative 4 over 2. Now the square root of 4, or excuse me, the square root of negative 4 is I times the square root of 4. The square root of 4 is 2. So as an imaginary number, this would be expressed as 2 plus or minus 2i over 2. And then that would simplify, let me put this over on the other side now, to dividing through by 2, 1 plus or minus I. Well, I guess I can write it here. 1 plus or minus I. So the solutions of our equation, that is the zeros of the polynomial, solutions and zeros, essentially synonymous for us, would be x equals negative 1 with a multiplicity of 3, x equals 1 plus I, and x equals 1 minus I. Including multiplicities, that's a total of 5 zeros. It's like saying negative 1, negative 1, negative 1, 1 plus I, and 1 minus I. Notice the non-real solutions, the 1 plus I and the 1 minus I, are conjugates, as they should be. Also notice that we shouldn't expect, after identifying negative 1 as a 0, we shouldn't actually expect to find any additional real zeros, because looking at the graph, it appears that there are no other x-intercepts of the graph. Real number zeros always correspond to x-intercepts, and it would appear that this graph has only one x-intercept. So, one real number 0, 2 non-real zeros that are conjugates, a total of 5 zeros if we count the multiplicity of negative 1, that is, if we count negative 1 3 times. That's a total of 5, which matches up to the degree of the polynomial in our equation. So that concludes the section 3.5 notes.